Let's begin with a question that might fracture your sense of scale. What happens to your idea of far away if 1 second equals 1 light year? That's the only rule in this experiment. A simple thought experiment, but one that will twist everything you think you know about the size of space. From now on, every time you hear a second tick by, you've traveled 1 light year outward from Earth. 1 second, 1 light year. Now, before we go anywhere, we need to make something very clear. A light year is not a unit of time. It's a unit of distance, the distance light travels in a single Earth year, moving at nearly 300,000 kilometers per second. Multiply that by a year's worth of seconds, and you get a distance of roughly 9.4 trillion kilometers. But that number is useless to your brain. That's because your brain, brilliant as it is, wasn't designed to grasp numbers like trillions. It evolved to judge what matters to your survival. How far is the tree? How fast is the predator? How long can you run without collapsing? Not, how far is Alpha Centauri? How big is the Oort Cloud? How wide is the galaxy? Your brain never needed those answers. Until now, so instead of trying to hold onto a number, we give you a feeling, a rhythm, 1 beat, 1 second, 1 light year. Let's begin. Second 0, you're still on Earth. Feet planted in gravity. Atmosphere buzzing with life. Signals bouncing off satellites. All the noise of civilization wrapped around a tiny planet in an ocean of dark. Second 1, you've just moved nearly 10 trillion kilometers outward. Congratulations. You've already left the solar system, at least what most people imagine the solar system to be. Earth is now a dot, too small to see. The sun, once the central furnace of your life, is now just another star behind you. But wait, isn't the solar system supposed to be big? You're right, but not that big. Not compared to a light year. At this scale, Earth to Sun is a joke. That distance, 150 million kilometers, is now less than a pixel in your rearview mirror. Even Neptune, orbiting at the edge of what most schoolbooks show as the edge of the solar system, is gone in a blink. You didn't glide gently past it. You blew right through. At 1 light year per second, the entire planetary system is less than a heartbeat. Second 2, you are now 2 light years from Earth. You've passed the region where any significant human technology has reached beyond Voyager 1. Beyond the boundary where solar wind gives way to interstellar space. Out here, there's nothing familiar. No planets. No stars close enough to recognize. And that's the first shock of deep space. Emptiness. It's not crowded. It's not buzzing with solar systems waiting for discovery. It's a desert. You're flying through nothing. And you'll keep flying through nothing for several more seconds. If this feels strange, that's because it is. You were taught that space is full of stars, planets, comets, drama, but that's a lie of perspective. The stars we see from Earth are incredibly far apart. They only look close because light collapses distance into points. Reality is more brutal. Space is mostly empty. But wait, we've been cheating a little, haven't we? Because in real life, you can't travel at 1 light year per second. Nothing with mass can reach light speed, let alone exceed it. According to the laws of physics, as you approach that speed, your mass increases, and so does the energy required to move you. In fact, to reach 1 light year per second, you'd need infinite energy. Nature says no, so let's fix this. Let's imagine you're not a spaceship. You're a free camera. Like in a video game, no mass, no inertia, just pure point of view. You're allowed to move through the universe with perfect freedom, as long as you don't touch anything. That's our loophole. The distances and structures you'll see are real, but you yourself are a ghost, observing, not interfering. With that rule set, let's continue. Second 3, you're now 3 light years away, still in the void. No suns, no planetary systems. Which might leave you wondering, where is the next star? The answer is, still ahead, because space isn't organized like a city with evenly spaced streetlights. It's more like a wilderness, occasional oases of gravity and light, separated by vast plains of silence. Second 4, now things start to change. Roughly 4.2 light years from Earth, lies Proxima Centauri, the closest known star to our Sunday. You reach it in just over 4 seconds. Proxima is a red dwarf, faint and small, but it holds a secret. At least one planet, Proxima b, orbits it in the so-called habitable zone. And here's the thing. We found that planet not by seeing it directly, but by watching Proxima wobble, just slightly, due to the gravitational pull of the orbiting world. In some cases, we see the star dim a little, just a fraction of a percent when the planet passes in front. That's how careful our instruments are, how hungry we are to find another home. But even if Proxima b could support life, it's unimaginably far. You just crossed the distance in 4 seconds, but in real life, with current technology, it would take tens of thousands of years to reach. Let that sink in. Every extra second in this journey is a distance that would take millennia to traverse with the fastest ships humanity has ever launched. And we're just getting started. Second 5. You're now 5 light years from Earth. Proxima Centauri is behind you, its dim red glow already fading into the dark. You've crossed the invisible line where the closest stars reside, and something strange begins to set in. There are no new stars for a while. You are truly, utterly alone. This is where we face a harsh truth. Even our local star cluster is mostly vacuum. The neighborhood, we live in the region of space that includes the sun and its nearby companions, doesn't feel like a community. It feels like an abandoned plane. The next few seconds will change everything you thought you knew about the solar system's edge, because you didn't actually leave the true boundary of our solar system in the first second. Not really. Let's rewind that thought. When most people say edge of the solar system, they think of Pluto, or maybe the Kuiper Belt, a field of icy debris beyond Neptune. That's where our textbooks usually stop. But those are just the outer lanes of the planetary racetrack. You're about to leave something much deeper. Second 6. 6 light years out, and now you've moved beyond the Oort Cloud, a vast, icy shell of comets that extends up to 2 light years from the Sunday. These frozen relics are leftovers from the formation of the solar system. Some of them get nudged inward and become the long-period comets that streak across our skies. But most of them, they float out here in silence, waiting. Now, here's something mind-bending. If we define the solar system, not by planets or comets, but by the reach of the sun's gravity, we arrive at something called the Hill sphere. That's the true gravitational domain of the sun, beyond which other stars' gravity dominates, and you passed that about a second ago. In other words, you've officially left home, not because you passed Pluto, not because Voyager sent a postcard, but because the sun has no more hold on you. Gravity, the invisible leash that bound you to our star, is now slack. It's an emotional moment, even in thought experiment form. This is where you stop being a solar traveler and become an interstellar one. Second 7. 7 seconds. 7 light years. You're now surrounded by stars you've never seen from Earth, not because they don't shine, but because they're too far and too faint. The farther you go, the less familiar the sky becomes. It's like walking out of your hometown into a forest with no trails. The constellations are gone. The sky is no longer a map, it's a blur of specks. And most of those specks aren't stars like the Sunday. They're smaller, cooler, dimmer. Red dwarfs dominate the galaxy. They're not flashy, but they're the most numerous type of star in the Milky Way, and each one may have its own family of planets. In fact, statistically speaking, there are likely more planets than stars. Many of them may be rogue, drifting freely without any sun at all, or orphaned from their birth stars during the chaos of galactic formation. Second 8. At 8 light years, you're still within what's called the local bubble, a strangely empty region of the galaxy that spans hundreds of light years, shaped by ancient supernovae that blasted nearby gas away, leaving a low-density void behind. In this bubble, there are still stars, still systems, still structure, but the interstellar medium, the cosmic fog that fills the space between stars, is thin. You are gliding through a kind of cosmic chamber of echoes, where the light of past explosions still reverberates, even if faintly. It's poetic, in a way, to leave your home and discover not a crowd, but a silence shaped by violence. Second 9. 9 light years gone. The bubble begins to feel less like a shell and more like a vast continent of space. And the stars begin to thin again. That's because stars aren't sprinkled uniformly through the galaxy. They clump, they form arms, clusters, voids, like weather patterns made of gravity and gas. You're passing into one of the quieter regions between those patterns. But look closely, and you'll see something incredible. Some of the stars nearby are moving together, not in a random drift, but in streams, arcs, trails. These are stellar associations, remnants of once dense star clusters that have begun to unravel as they orbit the galactic center. They're like cosmic breadcrumbs, left behind by the galaxy's own turbulent history. Some of those streams were only discovered recently by mapping billions of stars using the Gaia spacecraft. That mission has given us a kind of GPS for the galaxy, and thanks to it, we can trace the subtle dance of stars over millions of years, seeing not just where they are, but where they've been and where they're going. Second 10 light years out. And here's something astonishing. At this scale, 1 light year per second, you will cross the entire Milky Way in about 90 seconds. Let that sit with you. From end to end, our majestic spiral galaxy, so huge we once thought it was the whole universe, is a 90-second sprint, which means that what we call vastness is only vast by human terms. By cosmic terms, it's practically local. And this brings us to a strange, humbling truth. Our concept of far is broken. Even in this accelerated frame, even after 10 seconds of flight, you are still nowhere near the edge of the universe. You're not even close to the edge of the galaxy's disk. But you're about to start feeling the structure of the Milky Way, not as a beautiful swirl in a textbook, but as a lived experience. Second 11. You're now 11 light years out, and for the first time, you're flying through the Milky Way, not just looking at it from within. From Earth, the galaxy looked like a hazy river of stars, spread across the night sky. But now, at this scale, it feels like you're diving into an ocean of light, with dense, tangled currents, ribbons of stars, dust, and gas that stretch for tens of thousands of light years. But here's the twist. The Milky Way isn't actually dense. Not like you think. Even here, inside one of the spiral arms, the so-called Orion spur, the stars are still separated by several light years of empty space. Even at 1 light year per second, you're still mostly traveling through silence. Our galaxy is deceptive. From far away, it looks like a majestic whirlpool of matter. From up close, it's like fog made of glitter, beautiful, but sparse. Second 12. You cross 12 light years. Now you start to notice something else. Patterns. The stars aren't just scattered randomly. They form arms, spiral bands of density that sweep around the center like frozen waves. But they're not static structures. The arms aren't solid. They're more like traffic jams in a galaxy-wide highway. Imagine cars on a circular road. As congestion builds, clusters form, not because the cars stick together, but because they slow each other down. Spiral arms work the same way. They are density waves, not fixed objects. Stars orbit in and out of them over millions of years. Gas clouds get compressed as they enter, triggering bursts of star formation. That's why spiral arms shine. They are factories, not museums, and you're now flying through one of them. Every few seconds, you pass young stars, blue giants that burn hot and die fast, stellar nurseries wrapped in gas, supernova remnants that scatter metals into the void, seeding the next generation of stars and planets. Second 13, you're approaching 13 light years. More than that, you're riding the gradient of metallicity. Here's what that means. The farther out you go in a galaxy, the fewer heavy elements you find. The outer rim is older, simpler. The inner zones are richer, more carbon, more oxygen, more iron. Why? Because it's in the inner regions that stars have been dying and exploding longer and more frequently. More death means more recycling. More recycling means more building blocks for life. This is no accident. Where you are born in the galaxy affects what you're made of. Earth, by the way, was born in a sweet spot close enough to the center for rich elements, far enough out to avoid being fried by cosmic violence. A perfect balance, a Goldilocks orbit, not just in distance from the Sun, but in distance from the galactic heart. Second 14. Now the galaxy starts to warp, literally. The Milky Way isn't flat. Its disk bends upward on one side and downward on the other, like a vinyl record left in the sun. Why? No one is entirely sure. Some think it's the gravitational tug of satellite galaxies, like the Sagittarius dwarf. Others suspect dark matter is involved. But the result is a kind of galactic undulation, a wave frozen in time, and you're flying through it. Above and below you, faint halos of stars float outside the main disk. These are part of the thick disk, a more diffuse population of older stars that orbit differently than the ones in the flat, bright plane. From here, you can see how the Milky Way is layered not just in metal, not just in motion, but in age. It's like cutting through the growth rings of a tree, except the tree is 100,000 light years wide. Second 15. And then something changes. The stars grow denser. The light intensifies. Radiation levels spike. You're falling inward now, toward the galactic center. This is not a safe place. The core of the Milky Way is a maelstrom, an overcrowded arena of stars, black holes, and gas clouds moving at insane speeds. Here, stars orbit like comets. You pass one called S2, which flies around the center in just 16 years. That's absurdly fast, especially when you realize it's orbiting. Nothing visible. That invisible mass is Sagittarius A asterisk, the supermassive black hole at the galaxy's heart, 4 million times the mass of the Sun. And the proof of its existence isn't indirect anymore. In 2019, the Event Horizon Telescope produced a shadow, a real image, the donut that revealed the silhouette of the beast. That's not just theory, that's evidence. Second 16. You pass Sagittarius A asterisk. There is no event horizon here for you. You're a free camera, but you feel the pull all the same. Around you, stars scream past at thousands of kilometers per second. Near misses, friction, light twisted by gravity. And above you, the Fermi bubbles, massive lobes of energy stretching tens of thousands of light years above and below the galaxy's plane. Giant scars in gamma rays, left behind by a violent past when the black hole was far more active. Yes, our serene Milky Way used to be a quasar. The ghosts of that time still float above the disk. Second 17. You emerge from the center and rise into the halo. This is where things get invisible, because the stars here are sparse, but their motions don't make sense. They orbit faster than they should. That's how we knew something was missing. The galaxy's rotation curve is flat, meaning stars far from the center move just as fast as those near it. That defies Newton. Unless there's mass we can't see. And so we invented dark matter, not to explain a mystery, but to match an observation. We didn't want it to exist, but the galaxy's behavior left us no choice. You are now flying through it. It doesn't glow, it doesn't reflect, but it shapes everything. Second 18. And now you see the bigger picture. The Milky Way isn't an island. It's part of a neighborhood, a local group of galaxies. Some are dwarfs, some are faint, but one of them is anything but Andromeda, 250 light years away and counting down, because it's moving toward us. In a few billion years, the two galaxies will collide, not with explosive crashes, but with stars sailing past one another, their gases colliding, their black holes spiraling inward until they merge. A slow, graceful, cataclysmic ballet. We call the result Milkdromeda, and it will become our future home. But in the next part, we leave even that behind. What lies beyond Andromeda? The rest of the universe. Second 19. You've now traveled 19 light years every second for nearly half a minute. The Milky Way lies behind you, faint, sprawling, slowly vanishing in your rear view. But ahead, something looms. A blur of stars. A collision in slow motion. That is Andromeda. It's the largest galaxy in the local group, even more massive than the Milky Way. And as you coast toward it, something unnerving becomes clear. It's coming toward you too. In the real universe, Andromeda is on a collision course with the Milky Way. At this scale, that approach would be visible, measurable in seconds. We don't know exactly what the merger will look like, but we've simulated it hundreds of times. It will not be a single smash. It will be a gravitational dance, spanning billions of years. Stars will not collide. There's too much space between them, but their gas clouds will. That's where the drama unfolds. Friction, compression, shock waves, new stars igniting in great waves of light, and somewhere near the center, two supermassive black holes will spiral toward each other. Their final collision will shake the fabric of space itself, producing gravitational waves that ripple across the universe. You, however, do not stop to watch. You are already beyond it. Second 20 light years per second. You are now leaving the local group behind. This is a turning point in our journey. Until now, everything we've seen, planets, stars, comets, black holes, galaxies, was gravitationally connected, bound together in a web of mutual pull. The local group is like a cosmic family, held in orbit around a common center of mass. But beyond this point, the tug of gravity fades. Why? Because the expansion of the universe begins to matter more than gravity. That's right. Space itself is stretching, not pulling galaxies apart through force, but expanding the very metric of distance between them. This is cosmic inflation, still at work. And from now on, every second of your flight will bring you into increasing isolation. The galaxies ahead are not just far, they are receding. Not because they're moving through space, but because space itself is growing between you. This means there's a horizon forming a kind of cosmic point of no return, a limit to what can ever reach us again, not because of speed, but because of expansion. Second 21. You are now approaching the Virgo Cluster. It's the nearest large galaxy cluster, to us tens of millions of light years away, a city of galaxies, hundreds of them, dancing around a shared gravitational center. From a distance, it looks like a soft smudge in the sky, but as you get closer, the scale becomes crushing. The galaxies are enormous. Spirals, ellipticals, mergers in progress, giant black holes at their hearts, nebulas, X-ray jets, and something else, gravitational lensing. Space here is so warped by mass that light bends. You begin to see stretched arcs, like melted stars, around the largest cluster members. These aren't distortions of your vision, they are real deformations of space-time. Lensing is one of the strongest pieces of evidence we have for dark matter. We can see the distortion, but not the mass that causes it. The math doesn't lie. This is where astronomy turns brutal. The universe is not waiting to be observed, it's waiting to be decoded. And sometimes, what we decode makes us uncomfortable. Like this, most of the universe is invisible. Second 22. You pass through the cluster core. It's hot millions of degrees, not because of stars, but because of the intracluster medium, a diffuse plasma between galaxies that glows in X-rays. You can't see it with your eyes, but it's there. Enormous clouds of energetic gas, held in place by the gravity of invisible matter. It is here among the searing silence of plasma that you realize something disturbing. Galaxies are not the dominant feature of the universe. Gravity is, and gravity doesn't care about light. Second 23. You exit the Virgo Cluster. Now you're deep in the cosmic web, the universe's largest known structure. You might have heard that phrase before, but it's not a metaphor. The cosmic web is real. Galaxies are not sprinkled randomly. They are strung along filaments, threaded lines of matter, some hundreds of millions of light years long. These filaments intersect at nodes, forming clusters and superclusters. Between them lie cosmic voids, vast regions almost entirely empty. The structure is shaped by dark matter, seeded by quantum fluctuations from the first moments of time. You are now moving along one of these filaments, racing between clusters like a photon sliding through an intergalactic freeway. And the farther you go, the stranger it gets. Second 24. Now the filaments begin to blur. The density drops. You pass a region where baryonic matter, regular matter, is almost absent, but not gone, because scattered through these voids are thin, hot streams of gas, the warm hot intergalactic medium, or WIM. This is where we think a lot of the universe's missing matter is hiding. It doesn't emit much light. It's hard to detect, but it absorbs certain wavelengths of background quasars, tiny fingerprints, in enormous distances, and we're just beginning to map it. That's right, even the void isn't truly empty. Second 25. Your pace hasn't changed 1 light year per second, but the meaning of each second has changed completely. You're now thousands of light years from anything familiar. The galaxies around you are redshifting away, fading not because of dust or distance, but because the expansion of space is stretching their light to longer wavelengths. Redshift isn't just a measurement, it's a clock. The more redshifted the galaxy, the longer its light has been traveling. And you begin to notice the galaxies ahead are younger. You're looking back in time. Through your flight, you've turned space into time, and that means something profound is coming. Second 26. You begin to see galaxies that look wrong, too bright, too big, too early. These are the objects discovered by the James Webb Space Telescope, massive galaxies, from when the universe was less than 1 billion years old. Their existence is still puzzling. We don't fully understand how they formed so quickly. Some of them may not be real, or at least not what they seem, but some are confirmed, observed, photographed. They break our models. They whisper something we're not yet ready to hear. That maybe, just maybe, the early universe was more chaotic, more efficient, or more mysterious than we ever imagined. And the further you go, the less we understand. Second 27. You're now so far from Earth that even the concept of a galaxy starts to fade. The light around you is ancient, dim, filtered through billions of years of cosmic dust, redshifted beyond visible wavelengths. Some of it has been traveling for over 13 billion years, nearly the entire lifetime of the universe. And then, just ahead, a flicker of light that isn't a galaxy at all. It's something deeper, something older. You are now approaching the cosmic deep fields. These are not natural locations. They are human-made windows, regions of the sky, that telescopes like Hubble and JWST have stared at for weeks, collecting the faintest possible photons from the darkest patches of space. And yet, when we zoom in, they're not empty. They're bursting with galaxies, thousands of them, packed into the smallest sliver of sky. Some of the galaxies you're seeing here are only a few 100 million years old, not stars inside them, the galaxies themselves. Their redshifts are enormous. Their light is stretched so far, it now arrives as infrared heat, and by decoding this heat, we measure their distance. But more than that, their age. You're not just flying through space anymore. You're flying backward through time, because when light takes billions of years to reach us, we're seeing objects not as they are but as they were. Each galaxy becomes a fossil, a frozen moment in cosmic history. And as redshift climbs, something strange begins to happen. Second 28. The galaxies begin to vanish, not because they don't exist, but because they haven't formed yet. You are approaching an era known as cosmic dawn, the time when the first stars began to ignite in a universe that was, until then, completely dark. This is the twilight zone of existence, the period between the release of the cosmic microwave background and the first generation of stars, called population 3 stars. These stars were huge, short-lived, and made of pure hydrogen and helium, the only elements the Big Bang provided. No carbon, no oxygen, no metals. We've never seen them directly, but we infer their presence through chemistry. The second generation of stars, the ones we can see, contain trace amounts of heavier elements. That means something came before them, something massive, something that exploded. The ashes of these invisible giants are written into the next star's DNA. And here, in this silence before light, we find the universe preparing to become visible. Second 29. The light begins to fade entirely. Now, you've entered what cosmologists call the Dark Ages. Not the medieval kind, but a literal one. A time in cosmic history when light existed but couldn't travel freely. Why? Because the universe was filled with neutral hydrogen gas, which absorbs ultraviolet light. The first stars hadn't yet produced enough energy to re-ionize the gas and make space transparent again. It's a paradox. The universe was lit, but not yet visible. We're still trying to map this era using 21 centimeter radiation, a special kind of radio wave emitted by hydrogen atoms. New radio telescope arrays, spread across continents, are trying to catch this signal. It's incredibly faint, but if we succeed, we'll see the birth of the first structures, the first light, and maybe even the seeds of galaxies. This is no longer astronomy. It's cosmic archaeology. Second 30, and then, at last, you hit a wall, not of matter, not of galaxies, but of light itself. This is the cosmic microwave background, the oldest light in the universe, released just 380,000 years after the Big Bang. Before this, the universe was so hot and dense that photons couldn't travel. They were trapped, bouncing endlessly off electrons and protons in a superheated plasma. But then, something changed. The universe cooled just enough for atoms to form. Electrons latched onto protons, and suddenly, space became transparent. Photons were set free, and they've been traveling ever since. You're now passing through them. They surround you. A fog of microwaves, stretched by the expansion of space into a nearly uniform glow, 2.7 Kelvin, just above absolute zero. But look closer, and you'll see ripples, tiny fluctuations in temperature and density. These ripples are not noise. They are the blueprint of everything. From them, we infer the geometry of space, the contents of the cosmos, the seeds of every galaxy, the fingerprints of inflation. Even the total age of the universe is encoded in this light, 13.8 billion years. That's not a guess. That's a measurement. And you've just passed through it. Second 31. Now you are beyond light, beyond visibility. You've entered the recombination barrier, the final surface we can observe, not because there's nothing beyond it, but because light can't reach us from there. And yet, this is not the end, because before photons could fly free, the universe was still expanding, still cooling, still changing. And the events of that earlier time left an imprint not in light, but in the distribution of matter itself. So we turn to physics, to models, to mathematics, to guess what lies even farther back. Second 32. Now, you begin to feel the tremors of something strange. Inflation, a moment so brief, so violent, and so incomprehensibly fast that even at your current scale, 1 light year per second, you can't simulate it. Because inflation wasn't about motion. It was about space itself doubling in size over and over in trillionths of a second. Quantum fluctuations, tiny, random blips in energy, were stretched across the universe. They became the seeds of structure, where matter would clump, where galaxies would form. We can't see these fluctuations directly, but we can see their aftermath in the power spectrum of the CMB, in the distribution of galaxies, in the shape of the universe itself. Inflation isn't just a theory. It's the only explanation we have for the uniformity of space, the smoothness of the cosmic microwave background, and the vast structure of the universe today. But here's the part that still haunts us. Inflation might never have stopped, not completely, and that means, second 33, you might not be in the only universe. Inflation could still be bubbling, somewhere out beyond our cosmic horizon, spawning other universes, other laws of physics, other versions of time, space, and matter. In that view, what we call the universe is just a pocket, a single bubble in an infinite foaming sea of existence. You cannot fly to them. You cannot see them. But the math suggests they may be real. And so here, at the edge of time and light and matter and meaning, you are faced with the ultimate paradox. You've traveled further than any human mind has ever gone. And the one thing you've learned is that the journey never ends. Second 34. You are now 34 light years per second into the deepest journey the mind can take. And suddenly, you realize you're no longer seeing anything new. There are no more galaxies ahead, no more background glow, no scattered photons from the early universe. Everything has gone dark, but not because there is nothing there. You've reached what physicists call the cosmic event horizon, a boundary beyond which no signal, no information, no photon will ever reach us, no matter how long we wait. This isn't just a practical limit, it's a fundamental one. It's not the edge of the universe, it's the edge of causality. Why? Because the expansion of space isn't slowing down, it's speeding up, driven by a force we still don't understand, something we call rather helplessly dark energy. Second 35. Dark energy is not a particle, not a wave, not a field in the conventional sense. It doesn't clump, it doesn't dilute, it doesn't vanish as space grows. In fact, it does the opposite. As space expands, dark energy becomes more dominant because it's not tied to matter, it's tied to space itself. And the more space you have, the more of it there is. It's a runaway engine. And the result is that galaxies beyond a certain distance, about 46 billion light years, are receding faster than the speed of light, not through motion, but through metric expansion. We'll never see them. They're not behind a wall. They're behind a future that can never happen, a light cone that will never intersect with ours. You've reached the true limit of observation, not the edge of the universe, but the edge of what can ever matter. Second 36. And here, in this silent boundary, you begin to understand something quietly terrifying. You are surrounded by more universe than will ever be known. And that's not just poetic exaggeration, that's the literal truth. The majority of the cosmos lies forever beyond our reach, not because we're too weak, or too slow, or too primitive, but because of the way the fabric of reality is stitched. This is not just a place where telescopes stop working. It's where the very idea of observation breaks down, where even a light beam, traveling for eternity, would never reach us, where messages sent now would fall into a future that cannot reply. Second 37. This is where philosophy begins, because from this vantage point, you can ask the questions science cannot fully answer. Like, if we can never observe it, is it real? If no light can reach us, does it matter that it's there? And if the cosmos is expanding beyond all contact, what happens to meaning? This is not nihilism. It's liberation. It means meaning is not given. It is created locally, personally, temporarily. Meaning is what flickers in the brief window when consciousness arises, asks, and wonders. And right now, in this experiment, that consciousness is you. Second 38. And here's something even stranger. The further out you go, the more the illusion of motion breaks down. You're not really traveling anymore, not in the traditional sense. You're not flying through space, because at this scale, space is not static. It's expanding under you, behind you, around you. You're not crossing a distance. You're being carried by the expansion itself. It's like rowing a boat on a river, but the river is stretching as you row, faster than you can paddle, until rowing becomes meaningless. You haven't broken the laws of physics. You've just reached their edges. Second 39. And finally, a thought occurs. If the observable universe has an edge, then your life does, too. There are things you will never know, people you will never meet, versions of yourself you will never become, futures you will never live. And that's okay, because finitude is what gives shape to experience, what gives structure to choice, what gives weight to attention. A universe without limits would be a void, but a universe with boundaries is a stage. And on that stage, for the briefest of instants, something astonishing has occurred. A mind has arisen that can look back and say, I see. Second 40. You are now beyond the horizon, beyond light, beyond time, beyond cause and effect. And so, we return to the beginning. 1 second equals 1 light year. One beat of thought per cosmic span. It was never about reaching the end. It was about watching how the meaning of distance unraveled, how every far became close, how every number became feeling, how every structure revealed a mystery deeper than the last. You've traveled across the universe. But more importantly, You've reconstructed your sense of scale, your sense of wonder, your sense of what it means to exist in a cosmos that has no edge, no floor, no roof, only rhythm. And so now, as the final second ticks by, you arrive nowhere. And that is exactly where you were always going.